My idea is to give a very elementary talk about Bohm and GRW theory or collapse theories. And the reason is because these were two theories that Bell promoted a lot. That's the strange thing, is that many people still say, oh, Bell proved that Bohm theory is not possible because of the hidden variable theory. And actually, in his life, he was arriving to, like we heard from Tim this morning, arrived to the understanding of non-locality through Bohmian mechanics, because he said in this first paper on hidden variables, like Tim was saying, he said, yeah, this theory has a non-local character. Is this non-local character a feature of this theory? Is a general one? That's the question at the end of that paper before the famous one. And then in the famous one, he gave the answer that we heard this morning from Tim Modling. So my idea is to review the basic of this theory, the very, very elementary facts. Maybe there are more formulas in my slide that I want to comment. And in the next day, we shall have more technical talks on this, and especially concerning the relativistic extension of these theories. We'll have a talk on Wednesday by Professor Tumulka. And today, now I'm just speaking to the students, remember to go to the one of the three groups where many of the issues will be discussed in a focused way in each group. And so that by tonight, everybody will have a sort of common ground on the basic elements that are useful for following all the talks in this summer school. Actually, my intention was to honor Bell by recalling a talk that he gave 1 year before he died, a very beautiful talk. The title was Towards an Exact Quantum Mechanics. Was a talk in honor of Schwinger, and this talk and the article, the associated article, unfortunately is not in any of the collections of Bell's work. And I particularly like this article of Bell because it's stressing the importance of physical precision, conceptual and physical precision. That's why he's aiming towards an exact formulation of quantum mechanics. And since that talk was devoted to Schwinger, he starts the talk saying that it's a pity that in standard quantum mechanics, together with very high numerical precision, very high numerical precision in the prediction of a theory, this precision doesn't have a parallel in the conceptual foundation of a theory. And this is why he presented in this talk. This talk is 89. So one idea is to give you a flavor of what the situation was in 89. And let's say on Wednesday evening, you maybe have a full picture of what was done between 89 and nowadays, listen to the talks and going to the discussion groups. I will follow very closely the slides that Bell had. And yeah, I should apologize with Bell because I will not give, of course, the talk that he gave, but I thought that was a nice idea to review many of the things that he said in that talk and using his slides. Okay, this is just my slide because this is one of the problems that he raised just at the very beginning of the paper. What is the problem of quantum mechanics? And usually people say that the problem of quantum mechanics is the measurement problem, is the problem that was posed by Schrödinger in the cut paper that was mentioned before. The problem of the completion of description of a system provided by the wave function. If you are in a situation in which the cat is in a superposition of a state of being alive and being dead, then that superposition does not explain what we see around us. All the cats we see are dead or alive. And Bell was very humane, so instead of having a cat dying or being alive, he transformed, that is a transparency, is a slide by Bell. He transformed the problem into the cat drinking some milk and then having empty or full stomach, but the situation clearly is the same. You have the two states, A is empty, B is full, and then the superposition, which is a consequence of a basic principle of quantum mechanics, linearity. That superposition does not correspond to anything that we see around us. Okay, that's another slide of Bell, which is more humane than just poison entering in the room. And the presentation of Bell is such that is indicating that a deeper problem of quantum mechanics, of which the measuring problem is just a manifestation, is this. Is the fundamental ambiguity which is at the basis of standard formulations of quantum mechanics. Nobody knows what quantum mechanics says exactly, with underlining exactly, about any situation. For nobody knows where the boundary really is between the wavy quantum system and the world of particular events. This is the problem of quantum mechanics. So the problem of a Schrödinger cat is just a manifestation of this deeper problem of lack of a precise formulation, which Bell is describing in these terms. It's not a problem in practice, he says, because practice is not accurate enough and maybe never will be. But it is a conceptual and physical problem which we should worry about. And in other occasions, Bell was complaining about the complacency, how do you say in English? Complacency of theoretical physicists in accepting this basic ambiguity. He said, that's not a philosophical problem. It's a problem of physics. Try to formulate your theory with high precision, high conceptual precision. Try to aim at the same numerical precision that you have in your prediction. Try to do the same for the conceptual foundation of the theory. That's a vivid way of expressing the problem. No? There is no way of going from the micro to the macro. There is this wavy world on the microscopic level which just expand to the macroscopic one. And so that is the fundamental ambiguity that Bell is talking about. And this concerns not just non-relativistic quantum mechanics, but all formulation of quantum mechanics. Sometimes now I'm just talking to philosophers, to the young philosophers. Sometimes you hear in some philosophical circles that if you go to quantum field theory, even some physicists think the same. So that if you go to quantum field theory, then really the problems they are dissolved and you have other problems. No, the basic problem with quantum mechanics stays there, like it is in non-relativistic quantum mechanics. The problem of a basic ambiguity. And while many years ago, for instance, when I started this career, so end of the 70s, the common understanding was that there was no problem, that namely, we have to accept as a fact, as an experimental fact, was even said at that time, that we cannot do better. We have to live with that ambiguity. Because there are no other formulation of quantum mechanics that are empirically adequate and fulfill the desire of Bell, namely of being to have a precise formulation. You should stay with the standard formulation because the experimental facts tell you that you should do that. When I was a student, this is what was said. And indeed, nowadays, we can say the situation is completely the opposite. Indeed, there are many solutions on the market. Many solutions in the sense of Bell, solutions that provide an exact formulation in which there is not that problem that Bell is indicating. And here is the complacency of which I was talking before. This is another slide of Bell. And to get the flavor how to go to the formulation of these theories, we can follow this slide in which we have a situation of the problem of a Schrödinger cat there, and then how to solve it. So Bell is indicating three possibilities. The first one, okay, you may say, no, no problem. Psi is not real, so I should not find there, should not be worried. I mean, it's just, maybe somebody would say, just provide information. The cat is always empty or full, the stomach. But then if psi is not real, the natural question is, then what is real in your theory? That's the first. The second one, you can answer, say, psi is not all. Namely, at the end of your Schrödinger cat experiment, what decide whether the stomach is full or empty is not a wave function, but another basic variable that the quantum formulation neglects. That's the roads of theories like de Broglie-Bohm or Bohmian mechanics, namely the idea that the description provided by psi is not complete, and to obtain a complete description, you have to supplement the state description given by the wave function. You should supplement that with a description provided by, let's say, the actual position of the particle composing the cat, or the fields, or the string, or whatever, but something which is going beyond the description provided by the wave function. So will be then the configuration of point particles of a dead cat, the configuration of the fields, if you have a field description of a cat, the particular configuration of the fields that will distinguish whether the cat is dead or alive. But that is the road of Bohmian mechanics, namely to supplement psi with the actual position of particles. This is very good. It's the natural thing to do in non-relativistic quantum mechanics. And when you extend this theory to the relativistic realm, then you may have more options. You can, surprisingly, the best formulation I know is still in terms of particles. Namely, the basic ingredient that you have to add are still particles. But there are other proposals on the market in terms of fields or other structures. But what is important is these additional elements are there. The third option is that psi is not always right, meaning by this that the evolution of psi according to Schrödinger equation is not always right. It's not correct. If you follow this path, you're thinking of a solution of a measurement problem in which psi of a dead cat and psi of a live cat are such that even if they superpose for a very, very tiny bit, and then the dynamics force the wave function to go or to the dead cat or to the alive cat. But again, it's a problem of precision, because one might say that in standard quantum mechanics, you say, oh, that's more or less like that what I do. I say that I collapse a wave function. But the collapse of wave function in standard quantum mechanics is just what happens when you make a measurement. So you introduce at the most fundamental level such a very vague and macroscopic notion like a measurement. That's why Bell is asking, when exactly does it go wrong? Not just a a question of making a measurement, but elaborating a theory in which the wave function spontaneously, that means according to physical laws, goes or to the state of a dead cat or to the state of a live cat. Clear? And in addition to what I just said, I mean, that was the starting point, how to construct an exact formulation of quantum mechanics according to Bell. Bell is suggesting this, that in achieving this goal, you should be careful. And there are certain words better you don't use, because these words are, if you use them at the most fundamental level, you are introducing at the most fundamental level the ambiguity that is saying we should remove. And these words are system, apparatus, microscopic, macroscopic, reversible, irreversible, observable, information, for all practical purposes, measurement, written bigger than the others. Is it clear that if you formulate your theory using one of these, you may get into trouble? That means you may force at the most fundamental level the ambiguity that you would like to remove and not to have. Any question? I take a question during the talk. Okay, so if somebody wants to interrupt me, is welcome to do it. Yes? Are forbidden because I don't know whether I was clear enough in conveying the idea of Bell that in formulating a physical theory at the most fundamental level, I'm not talking about thermodynamics or information, I'm talking what we believe is the most fundamental description of nature. At that level, your formulation should not contain words which are ambiguous, which suggest a reference to an observer, to a measurement, because these are vague notions. That's why they are forbidden. I mean, it's just, he was a very kind person, Bell, very open-minded, and maybe he would have used a tone less, not arrogant, I don't think I'm arrogant, but I mean, it was, okay. But then in a very calm way, he would say, you should not do that. That means no matter what's the tone, the meaning is that. That would be bad.
Well, the answer is in your previous slide, because the distinction between the pair of words that are written there is just what in the previous slide you have said nobody knows what quantum mechanics
Sure.
say, because
that's what I said in word.
where to put
The shift is lipped. Yeah. But more than that, I mean, yeah, one, I prefer to refer, yeah, it's fine, I agree. But there is a basic ambiguity in using one of these words.
Well, I mean, maybe that would help. Just take the pair microscopic now.
Yeah.
In everyday life, they work pretty well. But if you ask exactly, if it was important to the physics, or how the physics works, whether the system you're looking at is microscopic or macroscopic, you ask exactly where is that edge, it doesn't have an exact edge.
Okay.
So these are just fuzzy words. And if you formulate your fundamental theory in terms of fuzzy words, you have a fuzzy theory rather than an exact one.
Okay. And now we see the okay words. Beable, and then I will have a few words to explain this word in later slides. Kinematics before dynamics. That means first be clear about the possibilities, and then talk about what are the laws governing these possible states of a world. Actually, that is what you learn in the first course in physics. When you take a course in general physics, first you say, okay, there are points, particles, matter points. They tell you something about the kinematics. That means They give you some mathematical tools to describe the trajectories, as curves, what is velocity, what is acceleration. So you specify what there is and how it behaves in a, without any, what are the main mathematical feature of a basic element representing reality, namely matter points. So they are trajectories that may have an acceleration, a velocity. You learn this. And then later you learn the dynamics. That means how the dynamical law constrains the set of possibilities. So the actual evolution of a dynamical system in Newtonian mechanics are only those that are consistent with the constraint provided by Newton's equations. So first be clear what there is, what is the mathematical description of what there is, and then give the laws of motion. So you learn this, it's very natural. First year you go to physics classes, that's the obvious thing. And then along the way, around the third year, fourth year, then things get tricky and professors seem to forget this distinction. Beables, I said that I wanted to give some idea about what they are, and for doing this I will use the word of John Bell. So, forget about what is there. I don't know whether that is relevant. But first, no, it is a bit relevant. I don't know whether I want to comment it. Let's read first what there is here. The terminology, beable as against observable. There is some humor here. I mean, it's not so serious. That we'll see. It's not designed, so it's an invented word, against observable. And somewhere say that they had some discussion at CERN what should be the right name. And then Zumino suggested beer, and then he said, no, but people may be confused if you say beer. So it was done in a humorous way. It's not in a naive metaphysical way. But that, at the end of the day, is one of the best contributions to metaphysics of the last 30 years, 40 years, the contribution of Bay. The terminology beable, so I read it in this way, is against observable, which is the word that you hear in a physics course around the second, third year. No? Before you had, the first year you get that nice story, Newtonian story, kinematics, dynamics. And then at a certain point, the student get, I think, confused. When I was a student, I was confused. That is not anymore the language, kinematics and dynamics. The language becomes observable. Quantum mechanics, there are the operators representing observables. The careful one, they say, represent observables. Usually they say there are operators that are the observables. Like in classical physics, there are the functions of space. Okay, it's not designed, this terminology, to frighten with metaphysics those dedicated to real physics. It is chosen rather to help in making explicit some notions already implicit in and basic to ordinary quantum theory. For, in the words of Bohr, and these are the words of Bohr, it is decisive to recognize that however far the phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms. Don't pay attention to the other part of the slide. I don't know whether I come back to that. The concept of observable lends itself to very precise mathematics when identified with self-adjoint operators. But physically, it is a rather woolly concept. It's not easy to identify precisely which physical processes are to be given status of observations and which are to be relegated to the limbo between one observation and another. So it could be hoped that some increase in precision might be possible by concentration on the beables which can be described in classical terms. And classical terms is in quotes, because they are there. The beable must include the setting of switches and knobs on experimental equipment, the currents in coils, and the readings of instruments. Observable must be made somehow out of beable. The theory of local beable should contain and give precise physical meaning to the algebra of local observables. In the slide before, you had some recollection of what, but I don't want to enter into algebra of local observer, whatever. Is it clear the project that Bell has in mind? It's just saying, look, and he's quoting Bohr, so in a sense he seems to use the arguments of the evil to define the good thing. Because Bohr always stressed the importance of having classical elements to interpret quantum mechanics. That this was forgotten by the followers. But in the formulation of Bohr, it's not just the wave function. So in a sense, Bohr didn't think the wave function was complete. For Bohr was essential the description of macroscopic objects using classical physics. So his point was not that the laws of classical physics are correct, but that the basic, because on the macroscopic level there are facts which are not predicted by classical laws. No, if you go around with a Geiger counter and all the macroscopic phenomena of the noise that you hear, all that phenomena is not explained by classical laws. But you should retain the classical concept, namely on the macroscopic level there should be notion like center of mass, position of objects, currents in a coil, that are meaningful. And you, according to Bohr, you should think of a quantum realm, something which you cannot talk about. That's the reason why the book of Bell is called Speakable and Unspeakable, so you cannot talk about what is going on the microscopic level, but there is a sort of image of what is going on there on the macroscopic one, namely the laws for the macroscopic objects are not the classical one. You make a certain macroscopic preparation procedure of a beam of quantum particles, and you get a macroscopic effect on a screen, which is not predicted by classical physics. But the macroscopic description of a oven that you are using to prepare the beam of particles and the macroscopic description of the beam, these are, when you do this, you're using concept of classical physics. What's the problem with this? The problem with this is that there is an ambiguity between the macroscopic scale and the microscopic one, namely the classical concepts that we are using on the macroscopic scale are not precisely defined. Even the evolution equation for this macroscopic variable are not precisely defined because they are somehow determined in a very not precise way by the underlying quantum structure. And here you get an example on the right-hand side of this quotation of how this could go. Namely, Bohr would think of a description of a quantum system in terms of two variables, the wave function and a set of macroscopic variables. But if you want to attain precision, the idea of Bell is that you should push these, not just keep it on the macroscopic scale, but go to all scales, so that you should introduce classical elements on the very basic structure of a word. And this X that I put here, so this structure is particularly clear in Bohmian mechanics. And you have an analogous situation in GRW, but there is not so dualistic the description like it appears here. But also there in GRW you are fulfilling the goal of attaining precision by making some variables precise, exactly characterized in all scales, and you don't refer to any macroscopic notion. And these are the beables on the very microscopic scale. That's at the beginning, this is another slide that you find in that nice talk of Bell. And until last night, I didn't want to put it. I thought I could skip it. But then since we had some discussion in a recent summer school where I was, and at least 10 of you were there, discussion about probability. I thought it was good to have also this slide. And okay, first say psi is not real, so what it is, this is the question. And if you say it's information, then information about what? So that for Bell, the answer is information. Is not a clear answer. And oh, it's just a way to generate probabilities. That's why I was referring to the school where we were. And I like this quote. Say, when von, can somebody help me to pronounce it? Bortkiewicz collected statistics on the kicking of soldiers to death by horses in the Prussian army in different years, he found the Poisson distribution. Now, you don't go out into the world looking for the Poisson distribution. You go out looking for soldiers and horses and kicks. That was just for the few of them that heard some talk about probability, but this is for everybody, okay? Now let's explore the two possibilities. Psi is not all, or psi is not always right. Psi is not all, like I said before. The next question is then, what else? What else there is? And De Broglie in 1926 and later on Bohm in 1952 rediscovered independently De Broglie ideas. The something else are just the particle positions. And the pilot wave picture that you obtain in this wave is by adding an additional dynamical equation, an equation for the positions of particles. And one way of writing the law of motion is just in this simple way. This should be here an imaginary part. This is a log. And this is assuming that the wave function is scalar valued. If a wave function were spinor valued, the equation you should use would be a bit slightly different. There are no jumps in this theory. That means there are just continuous evolution of psi, continuous evolution of the particles. You get a dynamics and mechanics, which has the same kinematics of Newtonian mechanics, but has a different dynamics. So that's the important distinction between kinematics and dynamics. So the sense is not, like some people say, a return to classical physics. You are just using the classical notion of the kinematics, but completely new equations for the dynamics. So the equation that you get is accounting for the quantum facts, and is just a different, so it's a different dynamics than the classical one. Belli says rational, it's clear, it's exact, agrees with experiment. And this maybe will be discussed in some discussion groups in the afternoon today and tomorrow, and then we may go back to some all together in the discussion section on Wednesday. Lorentz invariance, that is a question to which I will only, we keep repeating because there will be then a special talk devoted to elaborate on the status of Lorentz invariance of these theories, and there will be a working group devoted to explore the relation between locality, non-locality, and Lorentz invariance. I have nothing here. No, these I don't want to go into these details. No, not even that. I want to give a flavor of all theories and then no details. So now that was before was, let me adjust this to what we were before. That was in 89, so he gave a very short presentation of Bohr mechanics, maybe too short. And since 89, that theory has been analyzed in details. Some ideas that Bell had on how to explain how probability arise in this deterministic framework, where there's been a lot of work on that, especially by our group. I don't feel arrogant if I say that I think that what we did on the explanation with Shelley, with Detlef, on explanation of probability in quantum mechanics is probably one of our best work on the foundations. I don't know whether Shelley agrees, but I think he does. Even he's sleeping now. And there have been many attempts to explain how the operators, all the operator formalism arise, how to extend this theory to identical particles, to situations in which you have creation annihilations, and to quantum field theory, at least when the quantum field theory is well defined with some cutoff. So there has been work on that. And in the last 89, what is 15 years? No, I'm counting wrongly. 25?
Yes, it's 25 years.
I see. Time is
So
passed.
this talk is few months before the 25th anniversary of ICTP.
Yeah.
This year is the 50th anniversary of ICTP. It is exactly 25 years.
Okay, but there was a lot of work, okay? And GRW, the name's GRW, one G is here, Professor Girardi is there. R stands for Rimini and W for Weber. That was a paper they wrote in 1986, if I'm not mistaken.
Before the first draft.
The first draft. But for those that saw the published version, is 86 is correct?
It has been published as an ICTP preprint.
Ah, preprint, okay.
So it's 30 years
Okay,
from now.
30 years from now, okay. And they pursue a different path, not the path of adding something to the description of wave function, but the path psi is not right. By psi is not right means that psi in the world does not evolve according to Schrödinger equation, always. And of course, when you go into that direction, you should ask question, when? When then is not right? Which circumstances is not right? Now, don't ask me why he has 42 and 62, Bell. He's talking, I think, about some orbital. Okay, but as I said, there are two states, and so the question is when, I mean, because he's talking about situations, quantum states that are big enough to be close to the macroscopic, so there will be a splitting, the problem of saying, oh, the superposition is not anymore true, it's not anymore right, only the first or the second occur. And there was a long tradition in physics in saying, in giving some reason why that reduction occurs. There was the idea that the mind could do that. That was Wigner that proposed that idea. And then, of course, according to the orthodox formulation, the observer does it. And but when Wigner is very much associated to mind. When I was a young student like you, in 85, or no, it was 82, I went to a summer school, and I remember Wigner, at that time, abandoned completely the idea that mind would provide a collapse of a wave function, and he gave a lecture he was looking for an equation which would provide the collapse of a wave function. So that Wigner was exactly on that line of thinking that there should be a physical law, and not the mind, determine the collapse of a wave function. That was around 82.
Was an equation for the statistical operation.
Yes, well, he gave us, right. But when he was talking to us students, he had in mind that really should be the wave function. At that moment was formulated as a density matrix equation. But that was, it was already old, I mean, in that time, but so the tradition of that I'm talking about, psi is not right, at the end Wigner abandoned the mine interpretation, went in robot. And here there are the names, I mean, this is just, I'm following Bell's slides, so I don't feel responsible for missing, but this was 1989 was mentioned, of course, not your preprint, but 86 paper, the one, the physical value, the one that I also knew before you said that. And also Philip Pearl, and they provide these people a spontaneous wave function collapse. I think it would be fair to add also the name of Josi, Giancarlo, I don't know, but more or less was the same years, no, when Josi.
Also Carol Biaggi.
Okay, then no, I don't know him. Yeah, and yours. Yeah, Bell didn't have, but I would put also them.
Concerning Philip Pearl, he was considering stochastic and nonlinear modification. However, he had different modification of the Schrodinger equation according to the measurement that you are making. He was just mimicking the ruined gambler's game or something like that. And when he came to Trieste, I will say tomorrow suggestion of Bell, then suddenly understood the RWT.
Here a vague idea of how the theory is formulated according to Bell. I'm sure that Roderick Tumulka will give us more details. And just so everybody, so the idea that they developed is just this one, to find an interpolation between the Schrodinger evolution and the collapse. But then to construct a process for a wave function which does not disturb the microscopic system, because they want to keep all the beautiful prediction of quantum mechanics for the hydrogen atom, for helium atom, for whatever, but that on the macroscopic level will, the internal dynamics of the theory will be such that only one of the two BAMs, the dead cat or the alive cat, are selected. So they were looking for a theory, that means equation, not words, not talking not appeal to any observer, but a theory in which at random times, sometimes the wave function stops to evolve according to Schrodinger and evolves, jumps according to a specific law. And that in that slide you find the description of how, one implementation of the law. You can have more refined version, go into the continuous case, but I think that conceptually nothing is added to the original GRW formulation. Can be more useful, mathematically interesting, but the basic formulation is exactly what I say, to find that that does this. And to obtain such an evolution, that means you have to find one of the parameters, for instance, is this time, the time between jumps. And this has to be long enough that doesn't disturb the normal evolution of Schrodinger equation for microscopic system. But when you put many of them together, even a very tiny effect on one has the consequence of modifying and making the collapse of a wave function as a whole. I think you will have, or in the discussion groups or in other talks, more detailed presentation. I'm almost to the end of the talk. I wanted to give more details, but I will not give it because I'm thinking I'm running out of time. I didn't know I had that. I mean, the turning. Here, I want to say this, that here Bell is observing that the GRW jumps are spoiling symmetry. That means if you have a bosonic or fermionic wave function, the jumps will destroy that symmetry. Originally, this was one of the motivation for developing the theory in the quantum field realm. No, you had the evolution using quantum fields also to partly overcome this problem, if I'm not mistaken.
But for the identical particle, it was important But from the point of view of the localization, if you make the localization too sharp,
Yeah.
because actually most of the physics depend on the product of alpha when 1 over square root of alpha is the localization
Yeah.
times lambda, which is the frequency. So it is obvious that you can make it more frequent with a larger Gaussian is like to make less frequent with a narrower Gaussian. So essentially alpha and lambda enter with the product alpha lambda. However, 1 over square root of alpha is absolutely crucial because if it goes down to atomic dimension, it starts to producing dislocation in solid and something like that. And this, my friend of solid state matter tells me that would have already been discovered. So there is a limit on 1 over square root of alpha, not reach atomic dimension.
I want to say that since '89, many people have been working on this theory. Of course, Giancarlo and collaborators continue to do that. I mean, and then Bassi, that was your student, and Pearl, I think, continued, and Roderick Tomulka, that then provided one nice relativistic version of it, but also provided a formulation of a theory for which you don't need to go to fields to solve the problem of symmetry. He gave in the non-relativistic framework a formulation of a theory in which it is not this problem that Bell is pointing out. That means you can formulate the theory also for bosonic and fermionic wave function without destroying the symmetry of the wave function. Also here I gave a bit more detail about GRWF. That means, so far I talked about the theory as if all that matters was the evolution of wave function. Indeed, people working on this theory realized, and Giancarlo was one of the first, that to really provide a bridge with physical reality, you need the local beables that Bell was talking about a few slides ago. And namely, you need the stuff in space-time, which is governed by the wave function. And in GRW, you have many, while in Bohm, the choice is quite natural. I mean, you have a wave function, then you just add positions. And the positions are additional degree of freedom, namely, if you fix a wave function, you don't fix the trajectories of the positions. Here, all the local beables are such that if you fix a wave function, then what is going on in space and time is fixed by the wave function. And Bell, in one of his papers, again, one of the, what was, 87? Erice. Are there quantum jumps? Propose a very strange ontology, people say in philosophy, to call what there is. And what there is in space-time, according to Bell, are just the set of points around which the collapse happens. And since we need a name for this, just not to be confused, let's call it them flashes. And then the flashes will be a picture like that. That means if you look at the space-time description, these are the center where the collapse occurs. And if you take a macroscopic body, that will be really a very dense set of flashes in space-time. But why it's strange is ontology is when you just cut space-time with a space-like surface, maybe there is nothing there. So it's an ontology with not so much continuity in space and time. Okay. Another more normal ontology is to think of very more simpler terms, to think that the theory provides you a density of stuff, a density of matter in space-time, and the way to get this density of mass is just to do something like that, and namely to basically integrate out all variables in a configuration space except one, do this for all particles, and then you can get from a function of n points, a function in space, evolving in time, which is something that on the macroscopic scale can be associated to the normal density of mass, but on the microscopic one is just some density of stuff that is there. So in this way, the theory becomes a sort of classical stochastic field, non-local, non-linear, described in matter by means of this matter field. And I say that one of the problems is Lorentz invariance, both of Bohm and GRW. And I'm taking back from a different paper. This paradox, I'm talking about the problem of the Schrödinger cat. So these are disposed by the 1952 theory of Bohm, leaving as the question of Lorentz invariance. So one of my missions in life is to get people to see that if they want to talk about the problems of quantum mechanics, the real problem of quantum mechanics, they must be talking about Lorentz invariance. This doesn't want to diminish anything I said before. The main problem being lack of ambiguity. But once you understand that, that's a piece of cake. It's not rocket science, like Tim would say. To understand that these theories solve the measurement problem is something, really a piece of cake, easy. Now you have a serious physical problem. It's nothing to do anymore with conceptual issues. Of course, conceptual issues are relevant, but it's not a philosophical problem. It's a physical problem to understand the status of the theory when you go to relativistic realm. The big question, in my opinion, is which, if either of these two precise pictures, and the two that I was talking about, the two theories that Bell liked, can be developed in a Lorentz invariant way. And what has been done in the last, we say, 25 years, and not 15, like erroneously I computed, has been a lot of work in this direction. I hope that Roderick Tomurka will say something. Yeah.
Where did you take it from? Because I have it as a transparency of John when he delivered the lecture at the Bruno Tuschek lecture in Rome. But in 1990, Bell was already there. So.
No, that's where it was published. I don't remember, Giancarlo. I have to find out.
You should tell me, because
Okay.
I have it on one of the transparency of Bell at the Bruno Tuschek lecture.
Which sentence, Giancarlo?
Eh?
Which sentence?
The last
The
one.
last one.
Is it not against measurement?
No.
I don't remember, I must say. I have to check.
No.
I'm really going to the end. I always say the problem is Lorentz invariant. We shall discuss this in the next 2 days. I don't want to say more. I want to conclude. I don't even want to see what, I don't want to say, now, do I have 5 minutes? Yeah, we started 5 minutes late, so I think I have 5 minutes.
5 minutes.
So let me, before going, I wanted to conclude in the same way Bell concludes in that talk towards an exact quantum mechanics. But before that, I would like to summarize what are the key elements of what we call a precise quantum theory. This characterization covers many formulations. What Bell called local beables, we tend to call primitive ontology. And we give some additional meaning that at this level is not relevant. You can translate into local beables, that is stuff which is local in space and time. But since I'm familiar to this language, let me call it primitive ontology. So there is a clear primitive ontology. Translate into local stuff in space evolving in time, or local stuff in space-time, if you have a relativistic way of understanding the world. There is a state vector, psi, in Hilbert space that evolves either unitarily or at least for microscopic system very probably for a long time approximately unitarily. That's the situation of GRW. The state vector psi governs the behavior of a stuff by means of possibly stochastic laws. What does it mean? The stuff in Bohm are positions of particles. So the stuff is evolving along trajectories, and the wave function governs the motion of these trajectories, of these particles. And in GRW, the stuff is or the density of matter, what we call the density of matter that you get from the wave function of configuration space, or the flashes. Here you have a much more direct relation, and if you fix the wave function, the density of mass or the flashes are automatically determined. And that's what means to say that the state vector governs the behavior of a PO by means of possibly stochastic, because in the case of GRW are stochastic, and in other theories also could be stochastic. The theory provides a notion of typical history. This I didn't enter at all. Namely, we had some discussion in psych with the people that were there, so how probability, the usual probability, enters into the game. That is a long story that I don't want to attempt here. But this has to do with the notion of typical history, what is true for most histories. I will not say more. But there is a way in which physical probabilities, that are the one that physicists learn, again, always in the first year, namely relative frequencies that you observe in a lab, not just the probability theoretical that you assign to an event, but the concrete frequencies on which, when you go to the lab, you make the histograms, all these nice things. These facts are facts of the world, and nothing to do with except what is going on in the world. And then to understand why these frequencies, these empirical probabilities, are what they are predicted by the quantum formalists. But you need to explain that fact. And a nice explanation can be given within Bohm or within the GRW framework. And of course, the last requirement is that the probabilities that are predicted by the theory of a macroscopic configuration at time t agrees, at least approximately, with those of quantum formalism. Now, approximately means that you can have deviation. In GRW, you have deviation. So one virtue of GRW theory is to provide testable empirical consequences that are under investigation. Actually, there are some groups, like the group of Angelo Bassi, and other groups that are developing, also Giancarlo in the past made analysis of what could be the visible effect of the quantum jumps of the theory. Okay, that's all I had to say. And then let me end with the word of John Bella, just at the very end of Towards an Exact Quantum Mechanics. Now, in what I said, probably many of you think that I've been wasting not only my time, but yours. And therefore, I would like to end up on a more harmonious note with some concept of which we all approve. The theories that I presented to you are certainly not beautiful. I think they are not true either. It may be that they give some hint of where truth is to be found, but in their present brutally simplistic form, the truth is certainly not there. I do think, however, that they have a certain kind of goodness. These little spots are halos in the sense that they are honest attempts to replace the woolly words by real mathematical equations. Equations which you don't have to talk away. Equation which you simply calculate with and take the results seriously. Thank you, said Bell, and that was the last slide that he had in that talk toward an exact quantum theory. Thank you to you.